I think we should start. Hi everyone, welcome to the Foundation seminar. It's a pleasure to have Digvijay Wadekar here. He's a fellow at the IAS at Princeton, and he's interested in gravitational waves, cosmology, and astroparticle physics. And pleasure to have you here. Could you just hide the screen control lines? Yes. Yeah.
Automatically.
Yeah.
Okay. Thanks for the opportunity to give a talk here. I'm Jay Wadekar. So today I'll talk about this project in particular, which is like we did a search for black holes in the LIGO-Virgo data. I'm also interested in other things like using dwarf galaxies to constrain dark matter or machine learning applications to cosmology. But this talk will be focused on this particular topic. So this is work actually done with the people mentioned here. Teja Venumadhav and Ajit are at UC Santa Barbara. Javier is at Caltech. Barak and Jonathan are at Weizmann, and Matthias and Seth are at Princeton. And this is based on one of the papers I've listed here and some of the work that we are just going to submit soon. First of all, to mention that none of us are in LIGO, but we are thankful for the LIGO-Virgo collaboration that they release the data publicly and some of the analysis tools. So like people outside the collaboration can play with some of the data and see what they find.
Quick question. The video on Zoom is only showing a bit of the screen. Is there a way you can reshare it and share the whole keynote? Is it just
Yes, it makes sense. It's not good. Is it? It's not right. Oh, can you answer?
I think yes.
Okay.
Thank you.
Why did it say participant 0? Oh, 9.
9.
Okay.
So can you hide the?
Yeah. Okay, so just to give a very brief introduction, like we have till now in the gravitational wave data, we have found nearly 100 compact object mergers. A lot of them have been like binary black hole mergers, as you can see from the masses on the left-hand side. There have been a few neutron star black hole mergers so this is from the O3 data, which was taken a couple years ago. There was one GW170817, the binary neutron star merger, and then another one which did not have a counterpart. And this rate of like finding black holes will increase massively as we go to the next generation of detectors. So here I'm just showing like a cartoon of the sensitivity reach of current and future detectors. So currently we are at this O3. Now we have pushed a bit to O4. So we have observed like this was the first black hole that we observed. So this is like redshift, and we are pushing now into this 100 detection stage, and soon we will be like at these maybe like million detections per year or something when you have like this Cosmic Explorer or Einstein telescope. This is like LIGO A+, which will be around 2030s, so you can get an idea.
So are these dots actually expected mergers?
Yes. So this is from the rate model that they have fitted currently, okay. Our best guess of things. Yes, and I should mention, I mean, the reach of these detectors is like expected to be like around redshift 30 for these 30 solar mass plus 30 solar mass mergers. So we'll be observing like all the black holes up to the edge of the observable universe with these next generation detectors. And then I mean, I think like this slide put it in a good way, like all the different like physics that we expect to learn from observing these binary black hole or binary neutron star or neutron star black hole collisions. So we can have like very precise tests of extreme gravity scenarios that is listed in this panel. We can have like robust tests of these phase structure of quantum chromodynamics when we have like these neutron stars they collide, we can gauge the equational state of these neutron stars, and we will be able to infer that from future gravitational wave data. We can also know the black holes that are there astrophysically, the populations of black holes and neutron stars there are. What are the populations of different things? Where do they? What are the progenitors? Do they form in clusters? Do they form in stellar binaries or primordial black holes? And then, yeah, we have. I think we also, and this is like the most interesting part, that we could have unexpected discoveries in all of this, all of these things. Okay, so then, I mean, our work was based on like we developed a new pipeline to detect these mergers. So I'll talk a bit about data analysis, and feel free to like pause me at any point and ask any questions. Like just to give you an overview of what happens in a gravitational wave search pipeline. So in the first step, we have we build a template bank. So here is like one example. You have like the total mass on the x-axis and mass ratio on the y-axis. Each point corresponds to like a template here. Forget about the crosses and dots. I'll get to that later. So each point corresponds to like a gravitational wave waveform. We build this bank, and then we search over like the noisy interferometric data. And then this is the 150914. At places where you have like a very good fit, you have a large signal to noise, and then that is captured as a trigger. And so in the first step, what we do is like we convolve all these templates, and we get around 10 to the 5 triggers.
But the space of the library of waveforms has a lot of gaps, right?
Yes. So that's a good question. So they are actually more dense in the low mass range and less in the high mass. And the reason is like there are more cycles in band in the low mass range and not many in the high mass range, given the current sensitivity. So we need a fewer templates to match the signal. Versus here it becomes, the search is also much more expensive in the low mass range.
I wondered if the mass gap was actually left as a gap.
No, actually we do cover it. Okay, so after we get these quote-unquote triggers, we then try to see whether we are getting similar triggers in different detectors, because some of the times a lot of the times we get noise in individual detectors which can fire some templates. So we require that the same template should fire in multiple detectors around similar times. So for example, an event happens here, we know what the phase shift we expect and the time shift we expect between the signals in 2 detectors, and we can use that to rank them according to like what coherence they have. So the probability of them being of astrophysical origin versus them being of like being just noise transients. And after that, we then boil down this list to like 100 triggers, and these are the 100 triggers that are reported as like the tables that collaboration publish as the detection catalogs. And once we have these tables, we do parameter estimation on them. We run our MCMC chains. We know what are the time points which are interesting. So these are like around 10 millisecond to 100 millisecond like time points. You can run your MCMC chain with different waveforms, and then you get your binary parameters like masses, spins, redshift. Okay, so then right now what happens is like we use a lot of like sophisticated like waveform models in the final stage, this parameter estimation stage. And the reason is that it is much cheaper. I mean, this stage only involves like 100, so a very small amount of data, and you can use your sophisticated models which have things like spin orbit precession. For example, if your black holes, their spins are not aligned with the orbit, you can have the orbit like precessing as a spinning top almost. You can have some things like eccentricity, for example, when you have orbits that are not circular. Some of these effects are included in the final stage right now in the parameter estimation stage, and not included in this first part, which is this search stage, we call it, or the pipeline stage. And the reason is just data analysis challenge, like 100 triggers versus like convolving the full data, which is like a year-long stream data at 4096 hertz. And so this what might happen is actually if you only assume like very simplistic templates in the first case, some of the triggers which have these additional effects can actually get downweighted in our analysis, and maybe some of them not even enter this final catalog that we have. So that is the worry, and That is why we have been, our effort has been to include like some more effects into this first part of the pipeline.
So there could be more valid events. It's just that the template library is not big enough to include.
Yes.
Right.
So that will be the focus of my talk actually. We try to devise some methods to make it more viable. Yeah, so things like this, and then I think Hongsheng is going to present next week about another related thing where, so in this first step, we also are assuming like black holes and neutron stars, which we know, but then if there are like other objects like these super radiant clouds around black holes or boson stars or things like non-standard things, in some cases you could like miss some of these objects because your templates only are like these black hole or neutron star templates. So I will not go into these details, but yeah, just advertising his talk, I guess, here next week. And so we try to like also like devise a full like search procedure for objects like these. But okay, let me go to like the main part of my talk, which is these higher order modes. So apart from this precession and eccentricity, there is one another thing which people don't include in current template banks, which are these higher order modes. So let me give you an introduction. So we know the basic mode in this gravitational waves is the quadrupole mode, which is the 2-2. So this is like twice the orbital frequency. The binary goes around once. You have like 2 cycles of this mode. These are the H plus H cross polarization. And as you can see, this mode in the right hand plot, I'm showing like this 2-2 mode, and then I'm also like overplotting one another mode, which is the 3-3. So in the post-Newtonian expansion, the fundamental mode is the quadrupole mode, but as you go to like higher powers in V over C, actually just the next power in V over C is the 3-3 mode. So and then as you go further, there are more harmonics like 4-4, 3-2, all these things, and so on. And so like 3-3 is basically now like thrice the orbital frequency. So that's shown in orange in this panel, and you can see the sum of these is shown in black. So I mean, the motivation for our search was that if the true signal is black and you are hitting it with some template which is blue, you may miss some part of the signal. So like some farther away event which is near the threshold might just go below the threshold, or it might get ranked lower. And then okay, another thing, I mean, here I've shown like some simple formula to gauge when these modes become important. So the 3-3 mode, it actually it has a power over the 2-2 as a velocity. So it starts becoming more important close to the merger. So when like you are more sensitive to the extreme gravity case close to the merger. It also has different dependence on inclination, which I'll get to, and also like different dependence on masses.
Yeah, one thing I had. So in the previous slide, you showed different precession effects.
Mm-hmm.
So you can have orbital precession. The orbital precession vector also just precesses.
Yes.
So that is currently taken into account.
No, in parameter estimation stage that is currently taken into account. But in searches that is not.
So even the L precession is not.
The spins are in the searches. Spins are aligned with the orbital angular momentum. There is only the quadrupole mode. There is no eccentricity like that. Yeah. Okay, and then to just show you some motivation for like why we should include this is so here here is like the volume sensitivity that we lose if we do not include like some of these higher order modes. So I mean in this violet color we are not losing sensitivity. So this is the regime where like you have mass ratio 1 and low mass binaries where these higher order modes don't play any role. But then they start becoming important when you have mass ratios which are more extreme and binaries which are high mass, where you can start losing some. So this is like the fractional sensitive volume that is lost when you don't include these higher order modes in analysis. So you can lose up to like, for example, like 20% of your binaries at 200 solar mass and mass ratio 0.2. This would be a number. So before I get into the search part, I also want to like mention some of the physics related to higher order modes. So they are like this 5 to 10% of the signal as I showed you in the previous slide, but they are important still because they can break important parameter degeneracies. For example, this famous degeneracy, which is the distance versus inclination. So I people must be familiar. We like one of the motivations of these gravitational wave searches is like to find binary neutron stars and then we measure Hubble constants from these binary neutron stars. And for those we need actually like precise distance estimations, which we get like the luminosity distance directly from gravitational waves. But like for binary neutron stars, you only have like you have this degeneracy, so you don't exactly measure distance, you measure like combination of distance and inclination, and so that induces like more uncertainty in your distance, and that actually like hampers your determination of the Hubble constant from like binary neutron stars. So this was actually one of the biggest like systematic effect right now with measuring like Hubble constant with 170817. So people had to develop like all kinds of, I mean, you can say the jet is aligned, so the inclination is particular thing, and so then that breaks the distance versus inclination thing. But here, I mean, once you have like, okay, if you have good higher order modes, actually they break this degeneracy because, I mean, as you can see from this formula, the H33 has a different dependence on inclination than the H22, so it has the sine iota dependence. And that breaks this degeneracy. Again, this is also a picture that I just drew for the distance inclination degeneracy. So the binary, the waveform, the quadrupole waveform looks the same if the binary is face on but at a higher distance versus edge on at a lower distance. But higher order modes are different. Like you get 0 higher order modes here, but a lot of higher order modes in this case. So that can break this. Another point is like it can break the mass ratio versus effective spin degeneracy. So we want to be able to measure mass ratios accurately to constrain like the progenitor models of these black holes, and that also can be done using higher order modes. Yeah. Another thing that, as I already mentioned, these modes become important when you are like close to merger. So you can test general relativity in the strong field regime using these higher order modes. You can also like probe properties of remnants, like the recoil cake or the ring down spectrum, using them. Okay. So, okay, then to get to my like main point is like this searching with these higher order modes. Directly in the gravitational wave strain data. So why? So we already have been using these higher order modes for parameter estimation. So we have waveforms corresponding to this. We have had theoretical understanding corresponding to higher order modes since like 1970s, 1980s, but they have not been used till now in searches. And the reason is like more on the side of data analysis. So actually the template bank size increases by a factor of like nearly 100 compared to the like only using the quadrupole once you start including these higher order modes. So again, just this figure, I've just tried to highlight this. So what happens is like you have a 2-2 mode and a 3-3 mode, but the 3-3 mode depends on whether the inclination of the binary is like face on or edge on. That changes the amplitude of the 3-3 mode, and so when you combine them, you can combine these 2-2 plus 3-3 combination with different values of inclination, and then that adds like separate templates corresponding to all this. So you can have like multiple templates so you can just see, I mean, if I just make this 3-3 bigger or smaller, or if I shift it to left or right, that makes like a slightly different template each time. And so all these templates, if you do it naively, they all enter your template bank as I've shown on the right. And so this is like when you make a template bank only using the 2-2 mode versus the 2-2 plus higher order mode, you have like a factor of nearly 100 more templates. So this was actually one of the bottlenecks for doing this kind of analysis. And this point is similar also for the spin orbit precession or orbital eccentricity. As we are like, we make these waveforms more flexible.
So these are done analytically?
No. So these are all done, like there are approximations. So they have actually, the in-spiral is done using post-Newtonian expansion, and then there are some free coefficients which are fitted to numerical relativity simulations right now. Yeah, so all of these, yeah, there have now been, I mean, there is a big industry now which constructs like cheap waveforms which you can very easily query. You can just give total masses and mass ratio, and it can spit out a waveform very easily. So that is also available for both 2-2 modes, higher order modes, precession. But this is challenging, like how to use those waveform models to build a proper template bank and search in a reasonable like compute cost. So again, to mention the same point, like what previous searches I think have done is like they have made like say different combinations of these modes to make templates. So they sample over the inclination of the binary, which says the amplitude of the frequency.
Yeah, so these high order modes they are absent for the master one, right?
Some of them actually. The next one, the 3-3 mode is absent, but the 4-4 mode actually has does have small contribution for even for the mass ratio 1 binaries. Okay. You can understand it actually from symmetry. Actually, the 3-3 mode. I mean, if I just exchange the two masses and they are the same, you should get 0 in the odd multiples by symmetry. Versus in the even multiples, you should not get 0. Okay, so this is what I mean. Previous approaches have done, made these different like so for every 2-2 template they had like 100 templates, and then you have to convolve them with the data, and this is the most like intensive computational step. And I think like we could do it like I think much simpler. I think like I mean what we used was we used the intuition that you could actually instead of making like different combinations of these modes, you can convolve each of them separately with the data and get these SNR time series. So this is a signal to noise time series separately, and then actually just combine these signal to noise time series and get your final answer, which includes like all combinations of these modes actually, and that makes your data analysis much easier because now the cost is instead of being 100x as in my previous slide, now it just becomes like x. And I mean, and the reason is just that these three are like linearly added in your templates. So why not just match filter over them and then combine them rather than filtering over them separately? So yeah, this is like one of the things where we could like reduce the cost and we could do the full analysis using all these higher order modes.
So in this, do you also fit for the phase shift and the inclination?
Yeah, so all of that, like you can actually you get this SNR time series and you can just shift those if you want by different phases, or you can like shift them up by amplitudes to matter for inclination and marginalize over all of this in the final stage. And this is actually another thing we had to devise, but it is these are like some clever tricks to do in this case, which is but it's much cheaper than this case. This is the dominant like cost step is this step, which is the match filtering with the data. So
do you do it at this? Do you do it in that step?
Yeah, we do it in the second step of the phases and inclinations, all marginalizations. Okay, so I mean, I won't go into much of the details for these data analysis. Some of these data analysis things, like feel free to talk to me later. I'll mention like some other, like quickly mention some other things which are like offshoots that we can maybe use from this procedure that we have developed. So one of these things one could do better actually is like low latency follow up of particularly like neutron star black hole binaries. So right now, I mean, when an event happens, like you have your GCNs where you get like probabilities like this. So this is one of the events that I took from this website. So here, I mean, if you're an observer, this could be like an NSBH versus BBH. If you're a bit ambitious and you want to follow this NSBH, I mean, you still don't want to waste your resources on like binary black holes as you don't expect any counterparts from them. So like, I mean, if you make this prediction better, that can help observers whether to follow up these events. And like, if you make these numbers more precise, for example, rather than something like this where you have a lot of uncertainty. So from that motivation, I mean, these higher order modes, they can actually help in cases like this. And the reason is like these degeneracies that I had mentioned before, the distance versus inclination degeneracy and the mass ratio versus the spin degeneracy. So if I only include the quadrupole mode, which is what like current these low latency type analysis they do is. So
I mean, that's what LIGO does now.
Yes. Right. So they give you posteriors like this right now, which is like shown in the blue. So you have like broader posteriors than you would have if you also included these higher order harmonics. So I mean, this is like one particular case. Like this was 1914. This was like a NSBH candidate in the previous one. We are just showing this as an example, but so yeah, I mean, you are breaking this distance versus inclination and this mass ratio degeneracy, so you can have a better handle on the luminosity distance. So this can help observers to like search in the catalogs in a better way for events like this. And this also involves like I mean, there's the same step that I mentioned earlier. You can just add these instead of using just the 2 SNR, you can use the 3344 SNRs and get this very quickly actually. So I mean, this method can also be used in this EM follow-up way. And also for the another thing is also the masses. Like when you estimate the mass ratios more accurately, you can get the mass of the secondary more accurately. And so then you can decide whether to follow it up or not, whether like the low mass neutron stars have a more chance of producing an electromagnetic event. And so you would know, and this would give you a better handle on whether to follow it up or not.
So is there a reason you, so here you are showing 2, 2, 3, 3 and 4, 4, but like in these sorts of plots, you're also showing other modes. So when you say higher order harmonics, what exactly are you doing there?
Oh yes, we include, I mean, the signal to noise ratio is actually going down as you are going further in this harmonic ladder.
Right.
So we included only like these, the first 3, the 2, 2, 3, 3, 4, 4 and some other ones are there like a bit degenerate with some of these things. And you can go further, like when you go to like the LISA stage where you have the extreme mass ratio things, you will have all these things ringing like 5, 5, 6, 6, whatever. I mean, right now, given the current like signal to noise things, I mean, these are not very important.
So I meant the 2, 1, the 3, 2 type. So is there an ordering is there a hierarchy that they appear in? Like is the 2, 1 weaker than 4, 4, for example?
Like this actually depends on the parameter space, like depends on masses, like what mass. I mean, the 4, 4 is not very important at low masses, but starts becoming important at very high masses. The 2, 1 is like important in the intermediate kind of regime. So in our paper, we show that if you only include the 2, 2, 3, 3, 4, 4, we are like pretty accurate, not 100% accurate, but pretty accurate. Okay, so then another thing we also focused on, we were doing this higher order mode search, and we noticed that we would gain a lot for black holes like this in the high mass range. So then we were just curious, and we were like also looking into the noise properties of systems in this very high mass range, and then we actually found that we are actually quite limited by these noise transients. So these are called like glitches. Instrumental glitches in the data. So I mean, again, showing in this plot is like one of the, if you look at the spectrogram, so this is actually time versus frequency on the y-axis. I mean, people would have maybe seen, if you look at a binary neutron star, you can have a spectrogram which looks like a nice chirp. But for these high mass black holes, what is happening is you're only seeing the end of the chirp, like the rest of it is all hidden below. And so then, I mean, this end actually looks a lot like noise transients that are shown on the right hand side. So yeah, we are, I mean, in these detectors, there are many things that can produce these noise transients. It's an active effort to try to reduce these noise transients. And people have, there's like citizen science project. Here people have like given some funny names to these, like this is like whitefish, this is tomte, glitch, things like that.
Can I go back to an earlier statement when you said you can vastly increase the efficiency of calculation by taking the modes and comparing each separately with the full signal and then combining them? When you do that, do you reproduce the results that you get from the less efficient method? Do you capture the same?
Yes. I will show the detections. I should just get to that. I will show the comparison with the detections. We do capture a lot of the previous ones. Yes.
Not all.
Not there are some cases where things got vetoed, but I mean overall the number is like higher than I mean, yeah, I can show you the detection catalog. Yeah. So there is also, yeah, regarding your question, I mean, if the signal does have 0 higher order modes, you would like lose slightly the sensitivity to that. But so that's why I mean this higher order modes is like you have to do it precisely. Otherwise, if you just add more flexibility to your model where physically there is no possible signals in that regime, you would lose sensitivity. So it's like it's you have to do it precisely. we try to do it. I'll discuss about that. But first, let me just finish with these glitches, like the last part of our day. So, like for high mass mergers, I mean, these are the dominant things. I mean, just to give you a funny example, I mean, they can be like the reasons for these glitches can be very crazy. And in one case, they were actually like ravens flying over the desert, and they wanted, like, I mean, the pipes had some ice on it, so they pecked the pipes for water or something, and so that produced like some glitch like this. And then a grad student actually, I mean, had to go and then tap the detector at the place to try to replicate this thing. Things like these.
That's why he wore black to look like a raven.
One raven.
So it's a big challenge from the instrumental side, but from the theory side also, like we have to put in work to like remove this. And I mean, I won't go into details. We try to develop some techniques. We saw that our previous methods were not working very well because it's easy to like remove a noise transient when your signal looks like a nice chirp, but when it looks like a blip that I was showing earlier, it's hard to remove this. So we came up in some data analysis way. Like I will not mention. Like one of them is actually like removing bands like this, which are like wavering, and we call this like band eraser, for example. One of these tools that we have developed. Another thing which is also on the more data analysis side is like you are there are in your template bank, there are some of the templates are very clean, some of the templates are dirty. So clean in the sense that they don't catch a lot of glitches. So if the template is big, the waveform is longer, it's hard for a glitch to mimic it, but if the waveform is shorter, it's easy for a glitch to mimic it. So you separate those two things and you can get some better sensitivity. Yeah. Sorry.
We have 20 minutes with questions.
Okay. Oh, big question.
Yeah.
Sure. Okay. So like I should get to my like the new events that we found. So we are currently running like some parameter estimation runs on these. So we do two things. One of them is like introducing these higher order modes, and the second one is like the high mass sensitivity, which is dominated by glitches. We try to clean some of those glitches, and so we improve some sensitivity in the high mass regime. And so we found like some new things. So in this plot, I'm showing in the gray region. I'm showing like some of the events that all the events actually that have been previously reported by the LIGO-Virgo collaborations and also by other pipelines, including this. Like all these previous searches included this 2-2 mode, and all the results are shown in gray. So we recovered a lot of these things, but we recovered like some more signals as compared to them. And so for the signals that we recover, I'm showing them in this colored contours. So like the color of the contour actually corresponds to what is the probability of the signal to be of astrophysical origin rather than being noise transient. So you can think of them as like these red contours are like probability of half of them being real signals. So among two of them, one of them is real, one of them is a noise transient. We can't say it at the current level of sensitivity.
So what fraction of the grays did you miss?
Yeah.
Actually, so okay, among these nearly 100 ones, I think we missed around like 4, I think.
4. And you understand why you missed them?
Yes. So yes, we do. We do understand. So one of the things is like when you include these higher order modes, the SNR cutoff that you have to put was like slightly higher than the other one. So there were some things which are like low SNR which we missed, but that we could recover. I mean, when we were doing this higher order mode search for the first time, so we did not know like what bar to include. So once we include that, I think we can get some more events. One other thing that happened is like some of these got vetoed, like they have precession in them, which is the spin orbit precession. And in our pipeline, if a signal has some different characteristics than the templates, it can get like thrown out, considering it as noise. So that we have to improve a bit. Like we should not throw away precessing signals because they look different from our template, because these are also like astrophysically interesting. But but we do recover most of them. I can show the detection catalog later. So not just from our pipeline, there are also like other pipelines. I mean, IAS also had our 2-2 search, which we just released for the O3B case, and there is one another pipeline which is this OGC. We also recovered like some events from their pipeline. But okay, so then to focus on the new things, I mean, we expect when we include higher order modes and do glitch cleaning at these high masses, we expect like our sensitivity to increase at high masses, and we saw some things which are like some of them are like outside the region that these LIGO-Virgo events are. So you can see that these high mass ones are a bit different, and these are quite interesting. So I'll get into that. But another thing I should mention again, I mean, these are like the false alarm rate is like 1 per year for these events. So like all of them are definitely not real, but all of them cannot be noise. Like some of them are definitely real, and most likely the ones which are like green in this case. But yeah, they are not like super loud. I mean, the super loud events, I mean, LIGO already detects them. So those are shown in the gray contours. So we kind of like go close to the marginal events that we call in our pipeline. Okay, so then to relate to some physics, so there is this mass gap which from the theory literature, what people think is like you can have black holes. So like if your star becomes bigger than a particular size, you can have like pair production at the center, which actually ignites like oxygen or this carbon oxygen reaction, and that can completely blow away the star, leaving no remnant. Or it can follow these cycles and like reduce mass until it gets to like this 50 solar mass regime ballpark. So if your black holes are forming from this stellar collapse, you don't expect things to be between 50 solar masses and 150 solar masses. So you can have things below or above from this stellar collapse alone. And so this is like of interest, like this mass regime, because if you find some new things, I mean, and like this can shed light on whether these stellar collapse is like the only model to form these black holes. I should also mention there are some uncertainties related to this stellar collapse model. So, but like data driving this field, and in our case, we have also like found a lot of these. So this pair-instability gap is like this dashed lines between them. We found like quite a few events of like support in this mass gap events. Okay, and then.
But you're not preferentially more sensitive than LIGO. They have the same number of gray.
Yes. So in this range, no. In this range, yeah. But we will add more support to them to things in this range. Yes. But things outside, I mean, so there is also this open problem of like what happens after the mass gap right now, and so we have like some interesting events actually now which are like even traversing out. So this is pretty much the IMBH range, and this is pretty much uncharted from this 100 solar mass to like 10 to the 5, 10 to the 6 solar mass.
The definition of IMBH limit is getting by the LIGO people are like
What they can do.
Yes.
1,000 nominally.
For us, it's an ignorance. If you say 1,000, we won't be able to do it.
No, but that is the old IMBH definition.
Right.
You guys have
Yeah.
stretched it down.
Sure. Maybe the next detectors can do, but yeah, right now we can only.
But I mean, this one contour is one event, right?
Yes.
So Priya, you're saying that they keep increasing
No, they're bringing it down.
down.
Yeah. Into their
Or
purview.
they can detect.
So that they can claim they're seeing IMBHs.
Yeah. I mean, it's a definition. Yeah, like,
It's okay.
Yeah. Sure.
It's okay.
Anyway,
Where to get more
okay.
dollars.
Yeah.
Okay, another thing, I mean, if you notice here, there are like some white spaces. So if you just want to understand what is happening here is actually, so in the right hand top corner, things are going out of band. So LIGO is sensitive from like 20 hertz to like 500,000 hertz. So if you have black holes which are like high redshift and high masses, they can like just go out of the band. So they can be below 20 hertz.
And so I have a question about the probability that this is a real object.
Yes.
So you have two stages. One is your search, which is now you're now doing a little better job than previously. And then there's the parameter estimation.
Yes.
Is this probability after doing the second stage, or is it already at the first stage?
So the probability is entirely assigned by the search for all.
By the search, okay.
Yeah.
But then it will change, right? When you do a more serious parameter estimation, doesn't it tell you Some of them may even drop off and some may become much stronger.
No. So what happens is actually in the search pipeline we do analysis with the Hanford-Livingston, say like coincident analysis, and we do a background analysis also. So what we do is like we shift one of these detectors by an unphysical amount of time, and then we don't tell our pipeline that this is shifted, just do the full analysis. And all of the things we get from this are called like background candidates. And so then in our search, we rank our triggers based on what is the chance of a particular trigger in the coincidence run being similar to something in the background run. So for this parameter estimation stage, if you can do it for all these background candidates, you can have a estimate of what is the false alarm rate of these things. But parameter estimation is generally expensive.
And it's separate, right? It's it's kind of independent of the, except for the background events.
Yes, it's done. Yeah, so it's just costly. So it can be done on 100 things only. So for if you can make it cheap, so it can be done on 10 to the 5 things. You can have a false alarm rate, which is much more precise because it is based on the parameter estimation. But we don't have that, right? Yeah. Okay, so I mean, so if these things within these dashed lines I was showing, this pair instability mass gap, if they are not from like if they are not from stellar collapse, they can be from other channels which are like these dynamical channels. So here I'm showing like these two, the two most famous like channels for making these black holes, making these black hole binaries which can merge. So the first one is like the field channel. So here you have you have like binaries, and you can have like some angular momentum transport from one to the another, and then that actually can spin your black holes in the direction of the angular momentum of the orbit. So you can have like mostly aligned black holes in this case, versus if you form like these black holes at the centers of these globular clusters, they can like come up with, they can like make a binary with any random spin, and so the spins should be like isotropically oriented with respect to the orbit. So spins would be like one of the like distinguishing factors between these two channels. So what do we see? We actually so for the cluster channel, you should see things which are like symmetrically distributed about 0 in this plot, because they can be pointed up or pointed down. So this is just showing like the component of the spin, which is this chi effective thing, which is like what is the component of the spin along the direction of the orbital angular momentum. So yeah, here you can see like even for these high mass events, like there is like more preference for them to being like these spins which have like are in the component of the angular momentum. So that was like a bit surprising, because if you expect them to come from these dynamical channels, you expect them to have like these isotropic spins. We don't see that, but right now we are like exploring this. So to do this analysis, you need to do injections. You can, because this can also happen because if your pipeline is not sensitive to regions like this can automatically just happen. So we have to make sure that that is not the case. Our pipeline is also like sensitive to these low these negative spinning things.
So once again, you recover, what fraction of those from LIGO do you recover using your?
Yeah, I can show you the table. I mean, I mean, I don't have that, but I can show you like offline or something. It's okay. How much time? 10 minutes. Okay, so I mean, just to mention this point again, I guess for the spins, like we have a lot of like there is a big selection function that I showed in the previous plot where like the positively spinning ones actually so like they are like brighter in LIGO, and this effect actually becomes much more stronger for high mass systems. So I mean here I've shown just the amplitude of the strain versus the frequency, and so this is how signals look like with the positive spinning and the negative spinning things, and this green is like the noise curve for LIGO. So you can see that the positively spinning one lasts a lot in this nice band of the detector versus the negatively spinning one gets cut out kind of. So this, I mean, this in this plot, like not finding some systems could be just a result of these our selection, quote unquote selection biases, and so we are like looking into this.
But why is the difference?
Oh, so actually, like the positively spinning ones, they act, the spins act like a repulsive force close to the merger. So you stay in band a bit longer when you're close to the merger. Versus negatively spinning, you merge faster.
Much quicker. Oh, okay.
Yes, and that is very important because like these high mass ones, they are like the low frequency ones, and they are like very quickly going off band. And so yeah, this small effect can actually just like push them a bit on band.
So in chi-effective zero, it means they're anti-aligned, but chi-effective negative is they're like both spinning in the opposite direction of the orbital angular momentum. Right?
Yes, yes. I mean, chi-effective zero also happen if the spins are zero,
Right.
Individuals. Yeah. Okay, and then one another thing. Okay, this is my last plot. Is mass ratios. What are the mass ratios of some of these new events that we found? So from this higher mode case, I mean, as I showed you in the previous slides, these higher modes become important when you have like these more extreme mass ratio systems. So I mean, this is the plot showing like some of these systems. So we did recover. I mean, there are a lot of them we found were just. I mean, there are a lot of the systems that we found which are actually consistent with mass ratio 1, which means like almost equal mass things. But then there are like some which are consistent with this low value of mass ratio. So like our current, I mean, what we currently think is like we recovered these things. These things are not likely to have higher modes which have support in equal mass ratio ones. So maybe we just recovered them because of the high mass sensitivity increase because of glitch cleaning that we did. But these low mass ratio systems, maybe we recovered them because we included higher order modes in our analysis. So right now we are also like working on. I mean, we did these two things, so it's hard to say what made us recover this particular system versus what made us recover some other system. So right now we are like disentangling. I mean, in a new paper we like try to disentangle these effects and say how much like is added by just including higher order modes or other.
One question.
Yes.
Can you remind me what the status of NR waveforms is for different mass ratio than 1? Like, do people already have like very high?
Yes, that's a good question. So actually, yeah. So this depends a lot on whether you are assuming your spins to be aligned with the orbit or misaligned. So for the misaligned spins, we have like the parameter space is huge, and so we don't have a lot of waveforms. So right now the calibration of the waveform is done up to like mass ratio 1/4, 1/5 that limit. But for if you assume the spins are aligned, your parameter space is like much smaller. So people have done that up to like mass ratio 1/20, 1/18 kind of things.
So here there is a bias in some sort of selection bias because your waveforms don't have high mass ratio, high like different chi-effectives.
No, actually, so
or low mass ratio.
In our case, we are not including the spin precession effects. The only thing we have added is higher order modes. Spin precession. I mean, we are in this aligned spin approximation. Even in our search. Yeah, I mean, yeah. In the next step would be like try to make it more general and also include the spin orbit precession, but we're not there. So this was actually another bit of puzzle because I mean, if you expect like things to be in this pair-instability mass gap, they might have formed in the centers of these globular clusters. But the current simulations point to like for the mass ratio distribution of things in these globular clusters, current simulations actually favor them being close to 1. I mean, and the reason for this is like when you have these heavy black holes, they actually kick out these smaller black holes and try to sink towards the center. And so when you see mergers in the globular clusters, it's high chance that you have these heavy, both the black holes are heavy, which have sunk to the centers of these clusters. So mass ratio most likely is expected to be 1, but finding these things is pretty interesting for that scenario. So people can compare their simulations against this observed mass ratio distribution. So I should also mention, I mean, then we are like currently redoing these parameter estimations, and I put this question mark there because we did not find earlier systems which are like even low mass ratio things. But I mean, these contours have become like we are doing a better job of this, and some of them are actually even entering this stage. So yeah, I mean that's something in progress. Like, yeah. But this part is actually pretty interesting also. Like if you have very extreme mass ratio things, what is their distribution, where do they form. Like, I mean, it would shed a lot of light on the progenitor channels of these systems. I think I should just skip this. Okay, so let me just summarize. In the first part of the talk, I showed an efficient method for searching with these gravitational wave higher order harmonics, and I showed that our method is like 3 times more expensive as compared to the older searches that people have done. These 3 times instead of being like 100 times, which other people have tried to do this analysis by. And then we also searched in the O3 data, which is this previous data, which is public, and we found some new mergers with some interesting properties. And I should also mention, I mean, for next generation systems, these methods will be important as we are going to the more precision era. And also in surveys like LISA, where you have these extreme mass ratio in spirals, you expect to see a lot of higher order modes, and so this technique will be important. Okay, and the next step we are also thinking is like, so we have only included this one effect in our search, which is this higher order modes. There is also the spin orbit precession, which is currently an open problem. There is no search which is including the spin orbit precession. But this is an interesting astrophysical parameter space, because we expect this spin orbit precessing things to be in clusters, and so that's we are also like trying to get into this, maybe use like some old techniques, some of the same techniques that we have to make these searches like more computationally feasible, but that's a work in progress. And another thing we will do is like, we will from these catalogs, we will try to determine our selection functions and make this population level analysis of what is the mass distribution of black holes, what is the evolution of masses with redshift, things like that. We are working on it. Okay.
So, very, very interesting. Are there any new search events that you get for which the parameter estimation is an outlier or bizarre or odd?
Yes. So that question, I'm actually good segue.
Yeah, that guy.
Event. Yeah. So that guy you would expect. So I mean, one thing you would expect is like, if you have a high mass one, it should be bright, and so an high mass event which is like close to us, we should get a big signal from this. So why is this like not very strong? And the reason is actually spin orbit precession. So this actually does have like spins which are misaligned, and we found this after we did the parameter estimation stage. And so what happens, like, this is what happens like when you, if in your template bank you don't include these effects, and if a signal has these effects, I mean, the template bank thinks that this is just noise and it tries to like downweight it, and that's why this event got like a bit downweighted. Otherwise it would have been, I think.
And I guess from this plot, it looks like you can also extend to slightly higher redshift, detect higher redshift events that are that LIGO misses, right? So the guys in the upper above 1.2 or so.
Yeah.
So is there any reason for that? Is it just that it's like, it seems like you can extend the redshift horizon with a little bit more efficiency. Why is that?
Yes, so that's yeah. So actually, in the detector frame, we don't observe, like, I mean, the masses that we use for constructing templates, they are a combination of the source mass and time and the redshift. So it goes as like the detector frame mass is the source mass times 1 plus redshift. And so in the end, I mean, when we are sensitive to high masses, I am saying that we are sensitive to both high masses, high source masses, and also high redshift. So it both goes as a combination.
Or is it because of the 1 plus z?
Yeah, 1 plus Z.
Okay, I see.
Both goes as a combination.
Yeah, I haven't fully understood the procedure. So you're now including not just the 2-2 mode, but 3-3-4-4, right? You got a template bank with a whole lot of models. Each of them, I guess, the numerical GR has given you the exact waveform, right? Which includes all the harmonics.
Yes.
So what do? You take that waveform, you decompose it into 2-2, 3-3, 4-4.
Yes.
And then you pull those out and you separately do your cross correlation.
Yes, exactly.
Right. And then you're assuming that those waveform shapes not just shapes, the phase as well, is independent of the tilt angle?
No,
Isn't that the assumption when you do this calculation?
yeah, we can fold it in. So, I mean, once you perform this, you extract this 3-3 mode, for example, you make the signal to noise time series. And so then in the end, you can just like shift the signal to noise time series that you get, which accounts for the phase difference between in the waveform that you had earlier. So you can just, I mean, throw that step of the problem to the next stage, which is a cheaper stage than the first one.
I see. So you're basically saying in the first stage, you're really only looking for the amplitude of each of these modes to find candidates.
Yes.
And then in the next stage, you're looking at time shifts between them or whatever, relative amplitudes. All that is being pushed to the second stage.
Yes. Yes.
Okay.
Yes.
So would that mean that if you could move that second stage, also part of it into stage one, you would be even more sensitive?
No. So actually, our final detection is based on yeah. So I mean, this when you combine this, this is what is like used in our ranking. So this is when we like extract candidates and say that something is some candidate is better than background candidates that we have seen. We don't do it in this stage. But I mean, but the reason is like, I mean, when numerical simulation, so to extract waveforms, I mean, the 3-3 mode can just be bigger just because the inclination of the binary is a bit different. So I mean, like you don't want to run a full simulation again with some different inclination and then like run that against the data.
No, but you can wait, right, for all possible inclinations.
Yeah, you can do it.
Wait the 3-3.
Yeah.
That's what you do, right?
Yeah,
That's what you do.
we do. Yes.
I thought that when you are at the stage of adjusting the phases, that actually resolved the inclination degeneracy.
Oh, for the 2-2 mode, you're right. Like you don't have to any separate things because these are completely degenerate. Like the amplitude is completely degenerate distance. But this stops being a case when you have these 3-3 and 4-4. Like now the inclination is like weighting them differently with each other. Otherwise, I mean, for the 2-2 mode, you have a normalized waveform. You don't care about inclination. Just do the normalized waveform, get the signal to noise ratio. The waveform looks the same with the inclination. It's just going up and down. One thing doesn't matter, but if the relative thing changes, then it matters.
Eric has a question. Eric, do you want me to read it or do you want to ask it? We didn't hear you.
If you can hear me, I'll go ahead and ask it. So you said there were approximately 4 events that were detected using the standard search channels that your method missed.
Sorry, can you?
I'm sorry. Hello, am I coming through? I think you're muted, so if you're talking, I can't hear you. Okay, so good. You said there were approximately 4 events detected using the standard search channels that yours missed. I'm curious about how the signal noise ratio was affected. How many of the already detected events, the ones that the standard search detected, how many of those had their SNR according to your method significantly increased, and how many significantly decreased? And I'll mute myself.
So, okay, I mean, there was actually one of them which significantly got increased, and I mean, the reason was that even in the previous searches, when they found this event and then they ran the parameter estimation, they saw that there were a lot of higher order modes there. So this was like a nice candidate. I mean, we already knew that we were kind of like going to get this at a higher significance, and that's what we did. So this one event, one that I can remember, there are some which increased like mildly, but one of them was like significant, like a factor of 20 decrease in the false alarm rate for that one event. And then I didn't see any other event which was like a drastic reduction from the LIGO-Virgo false alarm rate prediction. So I think, I mean, maybe good thing would be just to like go through the table if you want. Like I have a I have a full table and I can show you if you want to compare like apples to apples, like all the LVC events and all the ones we detected and like compare their like false alarm rate one by one. You can do that.
Thank you.
So I had a question, which is a follow-up of probably Ramesh and and Peter as well. So if you were to do the 100 times more like expensive method, do you recover these events as well, like the new events that you find?
Oh, I mean, we didn't do this 100x.
So there are no other pipelines that do it in the 100x sort of
So
way?
there was one effort which tried to do this 100x, but then the template bank they had was starting to become very big. So what they did was then they just reduced their search to like a small chunk of the parameter space, saying that okay, higher order modes are only important for the face-on binary, so I'll only look at like plus 15 degrees, minus 15 degrees. So they have to restrict their search to that regime. But in our case, I mean, we don't have to restrict our search to this regime. So we are more general than them. But yeah, there has not been any other search. So for higher order mode, there has been I think 2 searches until now. The previous one I told you was like only these ranges, and ours is like the second one which has all range right now.
Are there any other questions on Zoom? Looks like not. So let's thank the speaker again. Thanks, everyone. We will see you next week.
So this glitch cleaning